Hello friends, welcome to my second lecture on methods for finding particular integral for second order linear differential equation with constant coefficients. In my last lecture, we were trying to find the particular integral in the case of the differential equation d square plus 1 by equal to cos square 1 by 2x, and we could not find it because we had to write cos square half x in the form of 1 plus cos x by 2, and when we write it in this form, what happens is that we have to find the particular integral for 1 by d square plus 1 cos x, but 1 by d square plus 1 cos x cannot be found from the formula 1 by d square plus a square cos ax equal to 1 over 1 over f d square equal to by 1 over phi d square equal cos ax equal to 1 over phi minus a square cos ax. We cannot find the particular integral in this case, because when we replace d square by minus a square, that is d square by minus 1 square or minus 1, this d square plus 1 on replacing d square by minus a square becomes 0. So, phi minus a square should not be 0 to apply this formula, and therefore, let us now discuss how to find the particular integral in the case of 1 over d square plus c square cos cx. So, let us discuss how to find the particular integral in the case of 1 over f d cos cx or 1 over f d sin cx, which are where in the exceptional case we have f d equal to d square plus c square, and we see that phi d square when d square is replaced by minus c square becomes 0. So, we are not able to apply the formula 1 over phi d square cos cx equal to 1 over phi minus c square cos cx. We will prove that 1 over phi d square cos cx, which is 1 over d square plus c square cos cx, gives us x sin cx over 2c. Okay, let us see how we do this. We can write 1 over d square plus c square as 1 over 2 ic, 1 over d minus ic minus 1 over d plus ic operating on cos cx, that is we break 1 over d square plus c square in partial fractions. Now, let us recall that we had proved that 1 over d minus alpha when operates on q, or you can say Rx, then we had e to the power minus alpha x integral e to the power alpha x e to the power minus alpha x into q dx. So, let us apply this formula here, and by using this formula 1 over d minus ic cos cx will be e to the power icx integral e to the power minus icx cos cx dx. Now, then what we will have is e to the power minus icx cos cx we can write as e to the power icx plus e to the power minus icx divided by 2 by the Euler's formula. We know that e to the power I theta is cos theta plus I sin theta, and e to the power minus I theta is cos theta minus I sin theta. So, from there cos theta is e to the power I theta plus e to the power minus I theta by 2. Now, this is equal to e to the power icx integral, this will be 1 plus e to the power minus 2 icx dx. Okay, let us integrate it, and we get then integral of 1 is x and then e to the power minus 2ICX divided by 2IC. Similarly, we can write the value of 1 over d plus IC cos Cx. This is equal to we get this. Now let us subtract from the value of 1 over d minus IC cos Cx the value of 1 over d plus IC cos Cx and then divide by 2IC. Okay. Hence 1 over d square plus c square cos Cx is equal to 1 over 2IC. From 1 over d minus IC cos Cx, we subtract the value of 1 over d plus IC cos Cx, and so this will give you x times cos e to the power ICX minus e to the power minus ICX divided by 2, and when we will have minus sign here, 2 becomes 4IC, and we get e to the power minus ICX. Here we get e to the power plus ICX. So, e to the power ICX plus e to the power minus ICX, and this is equal to 1 over 2 IC x times. Now, e to the power I theta minus e to the power minus I theta by 2 is I sin theta. So, we get I times sin Cx, and then here we have minus 1 over 4 IC. E to the power I theta plus e to the power minus I theta is 2 cos theta, so 2 cos Cx, and thus we have x sin Cx by 2c, and we have this 2 will cancel with that 2 here, so we will cos Cx divided by 4c square. Now, our differential equation is of the type d square plus a square by equal to cos Cx, d square plus c square y equal to cos Cx. So, auxiliary equation will be m square plus c square equal to 0. So, complementary function by hx will be equal to a cos Cx plus b sin Cx. And then when we will operate by 1 over d plus c square on cos Cx to find the particular integral. We get x sin Cx over 2c plus cos Cx over 4c square. So, this term cos Cx over 4c square can be absorbed in the term a cos Cx occurring in the complementary function, and therefore, when we write the result for 1 over d square plus c square cos Cx, we just retain x sin Cx by 2c. So, we say that since for cos Cx over 4c square can be absorbed, in yhx we have 1 over d square plus c square cos Cx equal to x sin Cx by 2c. And similarly, we can prove, we can show 1 over d square plus c square sin Cx equal to minus x by 2a cos Cx. Now with these formulas we can then find the particular integral easily in the case where phi minus a square becomes 0. For example, let us look at the equation d square plus 1 by e equal to cos square 1 by 2x. So particular integral by p x is equal to 1 over d square plus 1 operating on cos square x by 2, which we can write as 1 plus cos x by 2, which is equal to 1 by 2 1 over d square plus 1 operating on 1, and then we have 1 over d square plus 1 operating on cos x. 1 can be regarded as e to the power 0x, so this is 1 over 2, 0, d is replaced by 0, so we have 1, and then 1 over d square plus c square cos Cx gives x sin Cx over 2c, so c is equal to 1 here, so we have x sin x divided by 2 by using the formula which we have just proved. And similarly we can solve example 2. In the case of example 2, when we find the particular integral, sin square x by 2 is written as 1 minus cos x over 2, and then we apply the formula, same formula, 1 over d square plus c square cos Cx equal to x sin Cx by 2c to obtain the particular integral. Now let us look at another formula which is given by 1 over fd e to the power ax into b, where b is any function of x and a is some constant. So this when 1 over fd operates on e to the power ax into b, what we get is e to the power ax into 1 upon fd plus a operating on b. So this formula is very useful. In the case earlier we have considered 1 over fd operating on e to the power alpha x. This formula gives us 1 over f alpha e to the power alpha x provided f alpha is non-zero. But if f alpha becomes 0, then we cannot apply this formula. So the case where this f alpha becomes 0 can be handled by the formula which we are now going to prove. So let us see how we prove this result. When you find the derivative of the product function e to the power ax into b, you get e to the power ax into derivative of v plus a times e to the power ax into v, and this can be expressed as e to the power ax d plus a operating on v, and then you again differentiate, that is you find the second derivative of e to the power ax into b. What you get is if you find d square e to the power ax into b, then this is d of and derivative of e to the power ax into b we have found as e to the power ax d plus a operating on b. Let us operate by d. So derivative of e to the power ax is a times e to the power ax, then d plus a operating on b, then e to the power ax d operating on d plus a b. Now this can be expressed as e to the power ax, then we have a db a square b, so we can write it as d plus a whole square b. dd is d square b, and then adb, and then adb becomes 2adb, and then we have a square b. So a to the power ax d plus a whole square b we get, and thus if we apply fd operator, if we apply, suppose fd is equal to d square plus alpha d plus beta, okay, let fd be equal to d square plus alpha d plus beta, then fd operating on e to the power ax into b. will give you d square plus alpha d plus beta operating on this, and so what you will get actually d square plus alpha d plus beta operating on e to the power ax into b. So, this will give you e to the power ax e to the power ax d plus a whole square operating on b, then alpha times d plus a e to the power ax e to the power ax d plus a b, and then e to the power ax beta b, which is equal to e to the power ax f d plus a operating on b. So, this is what we get, and so thus ultimately we get f d operating on e to the power ax into b, it is equal to e to the power ax f d plus a into b. So, this suggests us this formula 1 over f d operating on e to the power ax into b equal to e to the power ax 1 over f d plus a into b. Now, let us see how we get this. So, we have to prove one over f d e to the power ax into b equal to e to the power ax one over f d plus a operating on b. Now, what we do is, let us operate by f d on both sides. So, operating by f d, f d and 1 over f d are inverse operators. So, we get e to the power ax into b equal to f d operating on e to the power ax 1 over f d plus a b. Now, let us look at the right hand side. So, let us assume that 1 over f d plus a operating on b is equal to b1. Okay? Let us assume that one over f d plus a operating on b is equal to b1. So, we shall get f d right hand side here will be equal to f d operating on e to the power ax into b1, and when f d operates on e to the power ax into b, what we had got earlier, that this is e to the power ax f d plus a b1. We have proved this earlier. Now, this implies that f d plus a, when you operate on both sides, you get f d plus a b1 equal to b. So, this will be equal to e to the power ax into b, and this is what we had to prove. This is the left hand side. So, right hand side and left hand side are same, and therefore, the formula 1 over f d e to the power ax into b equal to e to the power ax 1 over f d plus a operating on b is true. Now, let us apply this formula to this to solve this equation, d square plus 4d plus 4, which we can write as d plus 2 whole square y equal to e to the power 2x minus e to the power minus 2x. I will just find particular integral here. Complementary function is easy to find. So, this is 1 over d plus 2 whole square e to the power 2x minus e to the power minus 2x. Now, this is equal to, when 1 over d plus 2 operator square operates on e to the power 2x, we get 2 plus 2 4 square. So, we get 1 by 16 e to the power 2x minus, now when 1 over d plus 2 whole square operates on e to the power minus 2x, on replacing dy minus 2, d plus 2 becomes 0. So, we will apply this formula. So, we will, let us see how we get this. 1 over d plus 2 whole square we operate separately on e to, let us operate on e to the power minus 2x. So this is 1 over d plus 2, 1 over d plus 2 operating on e to the power minus 2x. We can assume here 1. So 1 over d plus 2 operating on e to the power minus 2x into 1. So b we are taking as 1. So this is equal to 1 over d plus 2 e to the power minus 2x. D will be replaced by d minus 2, and this cancels. We get 1 over d plus 2 e to the power minus 2x. 1 over d means derivative, 1 over d means inverse of the derivative, that is integral. Integral of 1 is x. Now again we will apply the formula which we have just proved to e to the power minus 2x into x. Let us take b equal to x. So then we will have e to the power minus 2x, d will be replaced by d minus 2. Now 1 over d is again integral of, we have to make integral of x. So that is x square by 2. So x square by 2 e to the power minus 2x, and thus the particular integral is. So this is how we can make use of this formula in the case where on replacing d by a in the expression 1 over f d e to the power ax, f a becomes 0. Now let us find another result. So now we discuss how to find the particular integral in case Rx is of the form x to the power m, where m is a positive integer. So when we have to find particular integral of this type, where m is a positive integer, what we do is, in order to evaluate 1 over f d x to the power m, we expand f d in ascending powers of d, and then operate on x to the power m. Since the derivative m plus 1 of the derivative of x to the power m is 0, and all derivatives more than m plus 1 are also 0, while writing the expression in the ascending powers of d, we need to write the derivatives of the powers of d only up to m. Rest of the terms will be 0. So we can evaluate particular integral by writing in the ascending powers of d. Let us see how we apply this formula. Suppose we have the equation d square minus d minus 6 by equal to 1 plus x square. So this is let's find particular integral here. So 1 over d square minus d minus 6 operating on 1 plus x square. 1 can be tackled again by writing e to the power 0x. So 1 over d square minus d minus 6 e to the power 0x, and then 1 over d square minus d minus 6 x square. So this is by replacing d by 0, we get minus 1 over 6, and this is okay, and 1 over d square minus d minus 6 when operates on x to the power 2, we have to expand it in the ascending powers of d, so that we can do like this: 1 over minus 1 over 6, 1 plus d minus d square divided by 6 raised to the power minus 1. Now we will expand it like we expand 1 plus x to the power minus 1. So this will be 1 plus x to the power minus 1 is 1 minus x plus x square minus x cube. Now x cube I am not writing, because x cube, in the x cube when you do d minus d square to the by 6 to the power cube, will minimum power of d will be 3, but we have x square here, third derivative of x square is 0, so we need not write those terms. We can stop here, and then okay, so this operates on x square, and so what we will get is minus 1 by 6 minus 1 by 6 and then x square, and then d minus d square when operates on x square, d on x square gives 2x, d square on x square gives 2. So, 2x minus 2 divided by 6, and then we have d minus d square when we find, we get d square, then we get d cube, then we get d to the power 4. So, d square when operates on x square gives you 2. So, 2 by 36. All other terms will contribute 0 because when they operate on x square, what we get is 0. So, this is the particular integral in this case. So, when 1 over f d operates on x to the power m, where m is an integer, we have to expand 1 over f d in ascending powers of d. Now, I will tell you how this expansion is justified. Suppose we have 1 over 1 plus d operating on x to the power m, and we are writing it as 1 minus d plus d square minus d cube and so on. We are expanding 1 over 1 plus d as 1 minus d plus d square minus d cube and so on, like we expand 1 plus x to the power minus 1. So, how this expansion is valid? Now, what you do is, to prove this, you operate by 1 plus d on both sides. So, operating by 1 plus d, we will have this. Okay. Now, 1 plus d and 1 over 1 plus d are inverse of operators. So, we will have x to the power m, and in the right side let us operate 1 plus d on 1 minus d plus d square minus d cube. What you get is, when you operate by 1, you get 1 minus d plus d square minus d cube and so on, and when you operate by d, you get plus d minus d square plus d cube minus and so on, x to the power m. So, these terms, they go on cancelling, and what we get is x to the power m. So, both sides are equal, and therefore, 1 over 1 plus d, if we write as 1 minus d plus d square minus d cube, like we expand by binomial expansion, this just expansion is valid, justified. So, when we have to find 1 over f d operating on x to the power m, we have to expand 1 over f d in ascending powers of d. Thank you.